Okay, I see video now. All right, and I see chats, messages. Excellent. Okay. Excellent. So we started with some, I don't want this camera. There we go. We started with some of Freebody diagrams and forces, talking about forces, some nomenclature that we use in our Freebody diagrams. We're going to start off today with a simple Freebody diagram of a book resting on a table. Okay, so go ahead and draw a Freebody diagram for a book at rest on a table. Okay, so when we get to the point where objects have dimension to them and they can rotate, then we'll draw our Freebody diagram of the object. We'll draw the shape of the object and where every force is being exerted on the object. And that helps us figure out if it's going to rotate or just move or whatever it's going to do. But right now, we don't have the tools to deal with things that rotate. So every object just looks like a point object to us. So right now, we can just draw a dot for this object. And then we can go ahead and put our forces there. So when I draw these Freebody diagrams, I was thinking about what's touching the object. Everything that touches the object may possibly exert a force on it. And then what can reach in from a distance. In this quarter, physics 4a, there's only one thing that can reach in from a distance and exert a force on your object, and that's gravity. So what's touching our object? A surface, right? The table. And surfaces can interact two ways, through a normal force and through a friction force. So in this case, we'd have a normal force. That would be the table acting on the book, right? And then we have no friction in this case because it's just sitting horizontally and there's no need for a friction force. If we pushed horizontally on the book, gave it a little push this way, then we would get some friction pushing back the other way. But if the book is just sitting there, there's no reason for it to have a friction force. And so that's everything that's touching our book. What can reach in from a distance? Gravity. So I'll write F sub G, and that's the earth on the book. Okay. Now let's make it a little more interesting. We'll have our table, we'll have our book, and we'll have a second book on top of it. So we'll have a lower book, and we'll have an upper book. So go ahead and draw Freebody diagrams for both of these. I'll start with the easy one. the upper book. We just did that, right? So we've got our book sitting here. It's interacting with a surface. It's not a table anymore. It's the lower book, but it's interacting with the surface. So it's the same thing as far as the upper book is concerned. That surface can interact through a normal force and a friction force. So that's the lower book on the upper book. And that's the only force acting on that book. It's at rest. So what can reach in from a distance? Gravity. That's the Earth acting on the upper book. Okay, now the lower book. Let's do that one. That's a little more interesting. So I'm trying to be careful with my subscripts here for at least the first couple of days we're doing this, and then I'll ease up a little bit. This is the lower book pushing on the upper book, right? This normal force is from the lower book on the upper book. This is from the Earth on the upper book. This is a free body diagram for the upper book. So every force here should be on the upper book. They should all end with this arrow pointing toward the upper book, right? U. So this next free body diagram is the free body diagram for the lower book. So every one of the subscripts should be on the lower book. So because these are all the forces acting on the lower book. So what's touching the lower book? The table is touching it. So it's going to push up. Normal force, table on lower book. And the upper book is touching it, right? Normal force. Upper book on lower book. That's all that's touching it. What can reach in from a distance? Gravity. And that is the Earth on the lower book. So what? So if we think about this a little bit, let's go back and take a look at these free body diagrams. And what we're going to learn very soon is that if there's a net force acting on something, that something is going to accelerate. Okay, it's going to move with acceleration. So if something is at rest, we know for certain there can't be a net force acting on it. So if we look at this first diagram here, what does that tell us about those two forces? They are equal in magnitude and opposite in direction. So N LU is equal to the opposite of FG Earth U. Equal in magnitude, opposite in direction. And then over here, it tells us that the normal force from the table on the lower book has to equal the sum of the other two, right? Okay. I guess I could write it right here. Sum of forces So this is the upper. This is the lower. And this is both together. We could view these two books as one big book, kind of replace these two big books, these two little books with one big book, right? So if we had that situation, if we had the table and then what would we end up with is that the normal force here is equal to F sub G, right? But what is F sub G? In this case, it would be F sub G for the lower book plus F sub G for the upper book, right? The weight of the lower book plus the weight of the upper book. And what does that tell us? These are two ways of saying the same thing. Question is about my nomenclature. This says that this and this are equal except for their direction, right? The direction is opposite. I wrote it as a vector equation. And this says that this and this, the magnitudes are the same. It doesn't tell me anything about the direction. Maybe they point in the same direction. Maybe they point in opposite directions. It just says the magnitudes are the same. Basically, two ways of writing the same thing. So if we compare this free body diagram for the two books as one to what we have up here where we split them up, we should be able to see that the normal forces, these internal normal forces, this one and this one are equal and opposite. So this should tell us that the normal force lower on upper is the same magnitude as the normal force upper on lower. Okay. So we'll get more into free body diagrams. And I'm hoping that I'm trying to point out here that these free body diagrams can be very useful. And so one of the ideas here is that it helps you spot which forces you know have to be the same, how they're kind of linked together, things like that, directions. So it helps you get the equation right. You know, it's a tool to help you get the equation right. The equation is what you need to solve the problem. All right, let's talk a little bit about Newton's laws then, so we can get into this. We don't need this yet. Okay, so all right. The first of Newton's laws is actually not Newton's idea, it's Galileo's idea. So Galileo died the year Newton was born, so they lived in that same time frame. And Galileo came up with this idea about inertia. So the first law is inertia. And it's said that Galileo was working with with ramps. He made an incline ramp like this. And he released a ball over here from rest. And he thought, how high up the other side is that ball going to go before it momentarily comes to rest and then slides back down? And so he released it from rest, and it went down, and it went up the other side. And what happened? It came to rest basically at the same height it was released from. And then he thought, well, what happens if I bend that ramp down so there's a much longer distance to go up the other side, and my ramp looks something like this, and I release my ball over here? Where's it going to end up? It's going to go way up this longer side until it gets to about the same height it was released from. And then he thought, well, what if I go one step further and I bend that ramp so it's flat? And I release my ball over here. What's it going to do? It's going to keep going forever. That is correct. That's what Galileo said. So we were stuck. Physics was stuck in the mid 1500s. This was around 1550. And not a lot of progress was made actually in the 2,000 years before that, from Aristotle back in BC times up to the 1500s. Not much progress was made. Almost 2,000 years, not much progress was made, because people didn't understand this concept of inertia. And when your foundation is wrong, you can't figure out what goes next. So what people thought was that, anytime you ever push on something, it comes to rest. And so people thought maybe the natural state of motion is rest. Maybe everything seeks to be at rest and tries to be at rest, and anything else just disrupts that. Well, Galileo kind of figured out that it's forces that are causing this change. And so if something is sitting at rest, it's not going to just get up and start moving on its own. It's going to stay at rest unless a force acts on it and makes it move. And conversely, if something is moving, it's not just magically going to stop. It's going to keep moving in a straight line forever, or until a force acts on it and changes its motion. And so that's the idea of inertia. And it is so important to understanding that, to getting to the next step, to understanding motion, that Newton restated that as his first law of motion. That is absolutely fundamental. Everything else builds on that. So that Newton restated Galileo's idea of inertia as his first law of motion. So when something is at rest, it stays at rest unless a force acts on it and causes it to move. If something is moving, it's going to continue moving in a straight line until a force acts on it and changes its motion. And his second law links some of these things together. So a lot of us write it this way, but it could be written a number of ways. Sum of the forces equals MA, or F net equals MA. It's the same thing, right? Or what might be better is if you write it this way: the acceleration is the net force over the mass. Question? So these all say the exact same thing, right? All say the exact same thing. But this third method, we typically write it like this, right? We write it as one of these ways, F equals MA, F equals MA. That's kind of the way we talk about it and think about it. But this is a little more intuitive in telling us what's going on. So if we want something to change its motion, acceleration is a change in motion, right? If we want something to accelerate, we exert a force on it. If we want it to accelerate more, we exert a bigger force on it, right? But inertia tells us that if something is at rest, it wants to stay at rest. It's going to resist those changes in motion. How do we measure inertia? Mass. Mass is how we measure inertia. So the more massive the object is, the bigger the force it takes to get the same acceleration. If I have a small mass and I exert a force on it, I can get some change in motion, right? I can get a certain acceleration. It's going to end up, maybe if there's some friction on the floor, I exert that force momentarily, the box starts to slide, and then friction slows it down. Eventually, the box comes to rest over here, right? Now I do the same thing with the bigger, heavier object. I exert the same force on that. That object starts to move, and then friction slows it down and stops it. Where's this one going to end up? Maybe here, right? I didn't get the same acceleration. I exerted the same force on both objects, but the big heavy one resisted that change in motion, didn't accelerate as much, didn't go as far. So the whole idea here is that it would take, to get the same motion with this bigger, heavier object, would take a much bigger force. Okay, so that's what this equation links those together, right? And it also links things like the acceleration of gravity. So let's say we were to drop two objects. We want to drop these two objects and see how they move under the acceleration of gravity. Which one hits the ground first, right? The light one or the heavy one? Well, they're both going to hit the ground at the same time. But one person might look at this equation and say, wait a minute, the bigger the object, the bigger the force of gravity acting on that object, right? What is the force of gravity equal to? It equals to mg. So this one has a big force acting on it. This one has a little force acting on it, right? So why doesn't the one with the bigger force hit the ground first? Well, it also has a bigger inertia, so it resists those changes. And it's, since the force is proportional to the mass and the inertia is proportional to the mass, they cancel out. Both of these objects accelerate at the same rate, hit the ground at the same time. Okay, Newton's third law. So Newton says that anytime two objects interact with each other, they exert forces on each other. That's what force is. It's an interaction. And those forces have to be equal and opposite. Equal and opposite. So when F the force from A on B, when object A and object B interact with each other, the force from A on B is equal and opposite to the force from B on A. If A pushes on B a little bit to the left, 2 newtons to the left, B pushes back on A 2 newtons to the right. Forces from an interaction, from a single interaction, are always equal and opposite to each other. Okay, so we could go back up to our free body diagram for the book sitting on the table and maybe pick out some forces here that might be a Newton's pair. So we have an upper book, we have a lower book, the Earth. Can we pick out some forces here that might be a Newton's pair? Third law pair. So Newton's pair tells us that the forces that result from a single interaction between 2 objects are always equal in magnitude, opposite in direction. So we've got some forces here that are equal in magnitude and opposite in direction, like, for example, these two right here. The normal force from the lower book on the upper book and the force of gravity pulling down, we know those 2 forces are equal in magnitude and opposite in direction. But the question is, are they a Newton's pair? And the answer is no, because they do not originate from the same interaction. The normal force is from the lower book pushing on the upper book. The force of gravity is from the Earth interacting with the upper book. These are 2 completely different interactions. If we had a free body diagram for the Earth, then there'd be a Newton's pair, this force with the one acting on the Earth. Those would be a Newton's pair. But we do have a free body diagram for the lower book. So there's a force right here, the lower book pushing on the upper book and the upper book pushing on the lower book. That is from a single interaction. Those 2 books are pushing on each other, maybe this way, pushing on each other. The lower book pushing up on the upper book pushing down on the lower book, equal in magnitude, opposite in direction. If we put a hand up here and push down on the upper book, what would happen with these 2 forces? They would both get bigger, right? The upper book would be pushing down harder on the lower book. This force would get longer. The lower book would have to push back harder on the upper book. This force would get longer. So you can see that those 2 forces are always going to be equal and opposite. But what happens if we push down on that upper book? This force now is bigger. The normal force just got much bigger, but what happened to the force of gravity pulling down? It stayed exactly the same, right? We didn't change the force of gravity acting on the book. So these two happen to be equal and opposite at this time in this situation, but they're not always equal and opposite. I could think of something I could do, like pushing down on the upper book here, that changes this, and those would no longer be equal and opposite. But these two will always be equal and opposite. No matter what I do, these two forces will always be equal and opposite. I could push down harder on the upper book. I could lift up a little bit on the upper book. I could do all kinds of things, and those two will always be equal and opposite because they are a result of the same interaction. Yes, so I think I answered the first question. If you push on the upper book, the normal force from the lower book increases. Yes, I think I answered that. Is this why if we kick the wall, we get repulsed by the wall? Yes. Yeah, you hit the wall, you exert a force on the wall is exerting an equal and opposite force on you. That's correct. Yes, in this case, the force of the table, here, we drew it here. The force of the table, that's this force right here, pushing up on both books. If we kind of think of the two books as being one big object, and the force of gravity acting down on the combined weight of both books, those two have to be equal because the books are not moving, right? And anytime, where's our Newton's second law? The acceleration is zero. If the acceleration is zero, that means, right, that if those books aren't moving, they're not accelerating, right? If the acceleration is zero, then the net force has to be zero. That's how we figured that out. So we said these books aren't moving, they're just sitting there. So the sum of the forces have to be zero. Well, there's only two forces acting on those. So we add those up, we have to get zero, which means they have to be equal and opposite. They have to cancel each other out. Yes, that's correct. Good summary of Newton's pair. Newton's third law pair, the pair of forces are from the same interaction, and they must always be equal and opposite. That's correct. I think really number one is probably all you need because that will dictate number two. But I think that's fine. Saying it like that is fine. Oh, one more thing about a Newton's pair. You will never find both forces of a Newton's pair in a single free body diagram. So I know it was tempting to say this force and this force are a Newton's pair because they're equal and opposite. But they can't be a Newton's pair because both of these forces are the forces acting on the upper book. Remember, a free body diagram only has the forces acting on that object. And in Newton's pair, one of the forces is acting on object A, and one of the forces is acting on object B. Those are the pair. So you have to have a free body diagram for object A and a free body diagram from object B to find the two. So if we have the upper book and the lower book interacting with each other, one of the Newton's pairs we would find in the free body diagram for the upper book. I put a red X on it. The other one we would find in the free body diagram for the lower book. I put a red X on it. Okay, so you have to have two free body diagrams in order to find a Newton's pair. You still might not have one, but you have to have at least two free body diagrams. normal. Yeah, you can link together here and figure out a lot of things. So question about these, whether these links. So the normal force from the table on the lower is equal to, yes. Yeah. You can, so that's why these free body diagrams are useful. Some of you are already trying to link together and seeing if is this normal force equal to the sum of the two weights of the books and things like that. And you're starting to link things together. And it's, I think a lot of that is because of the visual and writing out the free body diagrams first, and then some of the equations from those. Excellent. Okay, that's Newton's third law. We only have 6 to go. No, that's it. 3 laws. Although Newton was a busy guy. Newton did a lot of things. His laws of motion, 3 laws of motion here. He did a lot of work with light, actually, a lot of work with light. There's something called Newton's rings that you'll learn about in Physics 4C. What else did he do? He did gravity, the universal law of gravity. So out in week 10, we'll hit gravity, and we'll see Newton's universal law of gravity. And in between all of that, he invented calculus along the way. So he was a busy guy. All right, let's take a look at this situation. Have you draw some free body diagrams. So we've got a couple of blocks here. Crates sitting on the floor. Now I numbered them the other way here. Let me change it. Okay, so we've got a person pushing on 2 crates. And let's see, should we do... Let's do it with friction. So there's friction. And the person is pushing on these crates, and they're sliding across the room in this direction. Okay, so the person's pushing them. Let's draw free body diagrams for the person. Block 1 and block 2. So I think I'm going to start to drop all of those subscripts that I don't need. If you need to If you need to keep doing that for another couple of days, that's fine. Keep doing it to get in your mind what force is acting on what. But I'm going to simplify my subscripts a little bit. The only time I'm going to use a subscript is if I need to differentiate between two forces. You'll see here, I have two blocks in my system. So I might have a force of gravity acting on one and a force of gravity acting on the other one. So I wouldn't just put F sub g for both of them, because that would indicate that they're the same. So I'd have to indicate somehow F sub g1 and F sub g2. So I'll use subscripts to differentiate between two identical types of forces. But other than that, I think it's a little simpler to view it like this without all the subscripts. But it's a good idea to play with the subscripts the first day or two when you're doing these, maybe more than that, so that you start getting a feel for this is a force on this from that, right? That's the kind of thing we want you to spot. Okay, so did you do the person yet? Here's a dot that represents the person. What's touching the person? The floor is touching the person, right? So that could exert two types of forces. Normal to the floor, we could get a normal force. That's why we call it a normal force. So that would be this one. And so I'm going to put normal force P, because I'm going to have normal forces on other objects too. So this is a normal force acting on the person. And the floor can also interact parallel to the floor through friction, right? And what direction is the friction force acting on our person? Okay, hold it. What's the person doing? The boxes are sliding to the right. The person is pressed up against, their feet are pressed up against the floor, and they're pushing these boxes to the right, walking along the floor, pushing on them. Let's think about this. What would the person's foot do if that floor was frictionless right there? If underneath their feet, it's frictionless, what would happen to the foot? The foot would go sliding out to the left. Does the foot go sliding out to the left with friction there? No. So what direction does friction have to be pushing on the foot? To the right. We good with that? So you got a foot here. Yeah, that's not bad. You got a floor, right? And if that floor was frictionless, and this foot, the foot is pushing at an angle like this, right? If that floor was frictionless, the foot would go sliding out in that direction and the person would fall on their face, right? But there's friction there. So what is friction doing that's preventing the foot from moving in that direction? Friction has to be pushing this way. And our normal force is pushing that way. And friction plus the normal force together add up to be opposite of the force from the foot against the floor, because the foot's not moving, right? So there must be some equal and opposite force that's preventing the foot from moving. So the friction force is in this direction in this case. We okay with that? So I'm going to write that as static friction. We'll learn more about that today. And that's the only static friction force I have in my system here. So I'm just going to leave it like that. I don't need subscripts. It's the only one. Let's finish off our free body diagram for our person, and then we'll take a little break. Okay, so what else is touching our person? Block 1. So the person's hands are interacting with block 1. Block 1 is kind of like a surface, right? So they could interact in two ways, with a normal force pushing back on the person and with a friction force. But let's assume, let's make this simple, the person's pushing horizontally on block 1, not pushing block 1 down or up. They're just pushing horizontally. So there won't be any friction force, just a normal force from block 1 onto our person. I have a lot of normal forces, so I might need to indicate them like this. And that's everything touching our person. What can reach in from a distance? Gravity. So F sub G on the person. Question about the force between the hands and the block. So we've got a surface here, block 1, and we've got a hand pushing on block 1, right? So you can see that when the hand pushes on block 1 horizontal to the ground, the only thing that block 1 is going to do is push back on the finger, right, on the hand. So we get a normal force from this surface. We get a normal force pushing back on the hand. It's trying to push the block forward. The block's going to push back on the hand. But if the person is doing this, right, if the person's pushing down, but their hand is not slipping, right, then there must be some friction force pushing back up on their hand. So that complicates things. We don't want to get there just yet. And why is it static friction? Because the person's foot is not sliding across the floor. So when the person is standing on the floor pushing, there's no motion between their foot and the floor. It's static. Those two surfaces are not moving with respect to each other. If they were, the person's foot would slide out and they'd fall on their face, right? If it was kinetic friction, that would not be good for that person. Okay, so the only free body diagram I've drawn so far is the free body diagram for the person. So this is every force acting on the person. And after our break, we will draw the free body diagram for block 1. That'll be every force acting on block 1. That's going to have the force from the person pushing on block 1, right? And then we'll draw the free body diagram for block 2, and that'll have the force for every object. That'll have every force acting on block 2. Okay, so let's take a 10-minute break, and then we'll finish this up when we get back. Okay, so we are drawing free body diagrams for block 1 and block 2. Let's do block 1 next. Or block 2. Block 2 is a little easier. Let's do block 2 next. We'll do block 2. There's our block 2. What's touching it? The floor, right? So that's a surface that can interact 2 ways through a normal force, perpendicular or normal to the surface. Normal force acting on 2. And through a friction force. Now, if block 2 is sliding to the right, what direction is friction? To the left. And that's kinetic friction. Again, we're going to talk more about friction later, but I'm going to put a little K there. And I'm going to have another, I already know the answer. I'm going to have another kinetic friction force acting on block 1. So I'm going to put a little 2 subscript here so I can tell them apart. Okay, that's the floor. What else is touching block 2? Block 1 is touching block 2. So block 1 is causing block 2 to move to the right. Let's just call it a normal force could call it anything, F, whatever. let's call it a normal force. And this is 1 acting on 2. I've got a lot of normal forces, so I'm putting some subscripts there. And that's everything touching it, what can reach in from a distance, gravity, acting on block 2. Okay. And now we're ready for block 1. I'll give you a minute. So what's touching block 1? The floor is touching block 1. That can interact through a normal force and through a friction force. So if block 1 is sliding to the right, the friction force would be to the left. F kinetic acting on block 1. What else is touching it? Block 2 is touching it. So as block 1 tries to move to the right, block 2 pushes back against it. So I've got a force this way, normal force from 2 on 1. What else is touching it? The person is pushing it to the right. Normal force, I'm calling it. I'm just kind of viewing the hand like a surface, pressing on it. That's why I'm calling it a normal force. If you want to call it F push, call it F push. But I've got the person on block 1. That's everything that's touching it. What can reach in from a distance? Gravity. Okay, so if you look at these free body diagrams, this is the way I like to see them. Anytime I don't need to see all the subscripts and stuff. I know that all of these forces right here are acting on the person, right? I know that. And so I don't need to see all the little subscripts. And I know that there's only one static friction force in this whole problem. So I just have to call it static friction. I don't need to number it and give it a subscript and things. But I have 3 gravitational forces, right? 3 gravitational forces. So I have to distinguish them. Oops, I made a mistake on this one, didn't I? This is not 1. This is not 2. This is 1 right there, 1. So I have to distinguish them. So I put a P, a 1, and a 2 so that I can tell them apart. When I write my equation, I know that those are different, most likely, right? I guess they could be the same if they're the same masses, but most likely those are going to be different. I have 2 kinetic friction forces. Those are probably going to be different, so I label them 1 and 2, okay? So anytime you have 2 things that are probably different, give them different subscripts. Don't just label them the same thing. And you'll see that everything here is unique. What's the question? Oh, Good question about internal forces here. So the internal forces, what are our internal forces? We have things like, well, let's look at our Newton's pairs here. Should we mark Newton's pairs first? We've got, let me give you a minute to think about where are the Newton's pairs here. We have one of them is an interaction between blocks 1 and 2, right? Blocks 1 and 2 are pushing on each other. So I have block 1 pushing on block 2 and block 2 pushing on block 1. Those are a Newton's pair. That's a single interaction from those two blocks pushing on each other. 1 pushes on 2, 2 pushes on 1, equal and opposite forces. Okay, there's another one. The person and block 1, right? The person and block 1. So the person is pushing block 1 this way, and block 1 is pushing back on the person that way. So those are a Newton's pair. I don't have a free body diagram for the Earth. If I did, I could have Newton's pairs with some of the forces of gravity and the Earth, right? Those are interacting together, but I don't have a free body diagram for the Earth. Person 1 never touches block 2, so I can't have any interaction there, right? So I think I've got all of them here. So we know those are equal and opposite. Those forces are equal and opposite. Now, they're also internal to the system. So if you were to look at this thing as one big system, what's happening? How is it moving across the floor? Those internal forces always cancel out, right? They don't help the boxes move. The boxes pushing on each other, it doesn't help anything. You have to have something reaching into the system pushing at it. I like to say you can't make your car go faster by pushing on the dashboard while you're sitting in the car, right? That's not going to help you. You have to reach out, get your foot on the ground and push. Get some external force reaching in. Internal forces aren't going to help you go faster, right? So it's the same here. When we're looking at the overall motion now, we can think about what's reaching in from outside the system and causing the motion. So we've got these two friction forces are pushing back on us as we're trying to go forward, right? The two kinetic friction forces. So those are resisting our motion. And we've got the static friction force that's pushing in the direction of motion. So those are the forces we would need as we sum these up to figure out if this thing has acceleration or not, that kind of thing. Maybe it's moving with constant speed. Maybe there's acceleration. We would have to be given more information. Okay, let's move on. All right, let's take a look at this situation. So we've got a box being pulled by this rope attached to this truck. There's friction. The truck is moving, dragging the box behind it as it moves. And so you're going to pick from one of these directions, you're going to pick the best direction for each of these items here. So start with the tension force on the rope. The tension force from the rope on the box is closest to what direction? Tension force of the rope on the box. This is the rope on the box, right? So it would be pulling up and to the right. the rope is pulling the box up and to the right. Good? Normal force of the surface on the block. A, very good. The surface pushes normal to the surface, right? Perpendicular to the surface. Kinetic friction force. So this box is sliding across the ground, so we call that kinetic friction. And if the box is sliding to the right, what direction is the kinetic friction force? The opposite direction. And gravity. The weight of the object would be toward the center of the earth. Gravity pulls towards the center of the earth. E in this case. Okay, we okay with that? All right, let's make it a little more interesting. So we've got a person pushing a box that's sliding along the ceiling. They're moving to the right. The box is sliding along the ceiling. Okay. So first one, normal force of the ceiling on the block. Okay, very good. Right, a normal force is always normal or perpendicular to the surface. So that would be down. Surface can't pull on something, right? It can only push. Kinetic friction, ceiling on the block. The box is sliding to the right, so kinetic friction would be to the left. G. Good. So what they're going to do, they're going to view the hands like a surface, okay? And they're splitting it up. They're saying the hands are like a surface, and they interact with the box in two ways, through a normal force and through a friction force. So they're going to, first they're asking for the normal force from the hands on the block, and then they're going to ask for the friction force from the hands on the block. So if we treat the hands like a surface interacting with that box, the normal force would be what direction? The hands on the block, right? These are all the forces acting on the block. So the hands have, what would happen if the hands weren't there? So what direction are the hands pushing on the block? Yeah, there we go. A, up. If the hands weren't there, the block falls to the ground, right? So the hands are pushing up. And in what other direction are they pushing? What is up? A. And there's a friction force between the hands and the block, causing the block to move to the right. The block is moving to the right. Okay, if the hands were not there, would the block be moving to the right? No. So what's causing the block to move to the right? The interaction with the hands, right? So we're calling it a friction force because the hands are kind of stuck up against the surface of the box, but the hands are pushing the box to the right, making it move to the right because of the friction between the hands and the box. So the friction for the hands are pushing, what are the hands doing? The hands are pushing this way, right? And they're breaking it up into a normal force and a static friction force. So they're saying the hands we're treating like a surface. We know they're really pushing at an angle, but we're kind of breaking it up and saying that part of that force is holding up the weight of the box and pushing it into the ceiling. And part of that force is causing it to move in the direction it's moving. So that would be a C in that case, right? Are we okay with that? Right, they took this force that we know that the force from the hands is at that funny angle there, and they're saying let's view the hands like a surface. And the way we think of surfaces is they can only interact two ways, through a normal force and through a friction force. So they're splitting this into its vector components, the normal component and the horizontal component, the parallel component. If there was no friction, the hands would slide to the right. Yes, yes, but I think you're confusing the force of friction on the hands, right? The hand would slide, if there was no friction there, the hand would slide to the right. So there's a force of friction on the hands to the left. But what would the box do if there was no friction? It would not keep moving to the right. It would stay stationary. So the hands are causing the box to move to the right. So you have a box, you have hands, which we're viewing as there, that's a hand. So the force of friction is this way on the box, and the force of friction is this way on the hands. Okay. I think we covered the questions. If not, let me know. And then it says, why is it static friction? Why is the friction force between the hands and the box static, even though the box is moving? Yeah, there's no motion between the hand and the surface of the box, right? There's no sliding, there's no motion between them. They are stuck and moving together as one. So the interface there is static. There's no motion between them. Excuse me. And the direction of the Earth's force of gravity acting on our box is toward the center of the Earth. Okay. Okay. One thing I like to do is think about this, what I call a system schema. A schema is a diagrammatical representation, right? A diagram that represents something. So let's take something simple like, and maybe this will help you drawing free body diagrams and things, but I think it's very useful when we get to energy and work and thinking about what's interacting and what's in our system. So I want to introduce the concept here. But let's say we have a person standing on the floor. So here's our system schema, and here's our free body diagram. Person standing on the floor. We should be able to draw the free body diagram. Normal force, force of gravity, right? So for a system schema, we draw something that represents each object. So we've got our person, and we've got the building, earth, whatever we want to call it. I'll kind of combine those together. They're stuck together, right? The building is attached to the earth. So what is our interaction that's taking place here? The person has an interaction with the earth that's a contact force, right? That's the because the touching. Usually when we think about forces, there's a contact involved, right? Somebody comes up and pushes on your shoulder, you feel that force, right? And so for almost everything we deal with this quarter, there's only one, right? There's only one force that can reach in from a distance and interact with something, and that's gravity. Everything else, there has to be some contact. So this is a contact. The person's standing on the floor, and the floor is pushing back on the person because they are in contact with each other. That's the normal force here, right? And there's a non-contact force. That's the force of gravity. And so that's it, right? That's it. And I could draw, usually what we do is we define our system. So this would be our system boundary. And what we'll see later on is that when all the interactions are within the system, within the system boundary, then energy is conserved. So being able to define what our system is very important when it comes to energy and things like that. So it's a good idea to start to think about it a little bit now so that it's not completely new to us later on when it's most helpful. Okay, so when I look at this, I say these double-sided arrows represent interactions, right? This is an interaction of the person and the earth. This is an interaction of the person and the earth. So if I had a free body diagram for the earth over here next to my person, this one should tell me where my Newton's pairs are, right? And then this arrow will point out another set of Newton's pairs between the person and the earth. There should be 2 there, okay? So we could have, just for the, so you would know here, we could have defined our system boundary differently. I could have said this, person, earth, contact, non-contact. I could have drawn my system boundary here. And then what you see is that these interactions crossing the system boundary, energy not conserved. So you'd have to account for that somehow, right, in your energy conservation. Okay, so let's do one. Let's do one. It's pretty straightforward, but a little more interesting than a person standing on the earth. Let's do 3 boxes. Okay, so draw the system schema. And then we'll draw our free body diagrams for each of these boxes and the earth. And maybe you'll see where this is useful. So when I draw the system schema, I try to put the objects basically in the same orientation they are in the actual physical situation. So I'll put box 1 up here. And then I'll put box 2 underneath it. And then 3. And then the earth. I might need just a little more room there. So box 1 is interacting with box 2, right? They are touching each other. So we get a contact force here. And box 1 is interacting with the earth, right, through gravity. That's a non-contact force. That's our force of gravity. And box 2 is interacting with box 1, but we've already accounted for that with the arrow to box 1. And it's interacting with box 3 through a contact force, right? And it's interacting with the Earth through gravity. That's non-contact. Box 3 is interacting with box 2. We've already accounted for that. It's interacting with the Earth through a contact force, right? It's touching the floor. And there's a non-contact, the force of gravity, with between box 3 and the Earth. So those are our forces. If we wanted to define our system as being the whole thing, usually we like to include the Earth, make the system the whole thing, because it's a little easier that way. But for these purposes right now, the system is not as important. The system is important when we get to energy. All right, so if I look at my system schema, how many interactions are there with box 1? There's one here, and there's one here. 2 interactions. So how many forces are going to be in my Freebody diagram for block 1? 2 forces, right? I should have 2 forces. So when I go back and look at this now, box 1, what's touching box 1? Box 2, right? So there's going to be a normal force pushing up on box 1 from box 2. Normal force. 2 on, I've got a lot of normal forces here, so I'm going to go back to these 2 subscripts. Otherwise, it'll get really confusing. And what's pulling down on this? Gravity. That's the Earth on 1. And that's it. Two forces. Now let's look at box 2. I'm expecting to have 3 forces in my free body diagram for box 2. And if I draw my free body diagram, what do I get? Three pushing on 2 up. And down, I've got the normal force 1 on 2. And I also have force of gravity, Earth on 2. And then I could move over to box 3 and do the same thing. And what do I have? I've got a normal force 2 on 3 and F sub G Earth on 3. And then I've got the Earth. I've got a normal force 3 pushing down on the Earth. And I've got 3 forces pulling up, right? I've got F sub G 1, F sub G 2 on the Earth, F sub G, it's hard, let me spread these out. This is getting a little messy here. How's that? A little bit better. Now, the reason I like this for doing free body diagrams, let's take a look at the Newton's pairs. So the system schema is already telling me where all the interactions are. So let's see, I'm going to use, let's start with red here. So this is going to give me a Newton's pair. between block 1 and block 2. There's a contact force between block 1 and block 2. So 1 pushing on 2 and 2 pushing on 1, that's a Newton's pair. Then I come back up here and I say this one, I'll use two lines for this one. This is going to give me a Newton's pair with the Earth, right? This is the force of gravity with the Earth. So I've got this one and one in the Earth and one. Those are a Newton's pair, right? Then I come back up here. I'll use 3 lines now. That's going to be a Newton's pair between 2 and the Earth, right? The force of gravity and the force of gravity. And then I'll use 4 lines for this one. That's 2 and 3 are interacting with each other. Right, those are interacting. What else do we have? I'll use an X now. An X for this one, that's between the Earth and block 3, force of gravity. And then I have one more over here. So you see how this helped me spot all the Newton's pairs. So if you look at the system schema in relation to your free body diagrams, it really helps make sure you have all the forces right, and it helps you spot Newton's third law pairs. Okay. No, it doesn't. The question is, does that only work if the system's at rest? No, it works all the time. Okay. The boundary. Oh, so the boundary is your choice, right? How you define the system is up to you, but it changes how you solve the problem when it comes to using energy to solve problems. So we'll get to that more when we get there. So right now, don't worry about the system boundary. But when we get to energy in a couple of weeks, then we'll start talking more about that system boundary and what it means and how that changes our equation when we have an energy, when we're using energy to solve a problem. Does the third law only apply when the object is at rest? No. The third law is always true. If 2 objects are at rest and they are interacting with each other, the forces are equal and opposite. If they're moving at constant speed, the forces are equal and opposite. If they're accelerating and they're interacting with each other, the forces are equal and opposite. Anytime 2 objects are interacting with each other, the forces are equal and opposite. Always true. Always true. Good question. Okay, let's do time for one of these, I think. Let's do this one. We've got these 5 boxes on a conveyor belt. Okay, different masses, 5 different masses on this conveyor belt moving along at constant speed. And it says at the instant shown, the velocity for all of them, 2 meters per second to the right. They're not slipping on the belt. Okay, what's the net force on each of these? Okay, the answer is all the same, all 0, right? because there's no acceleration. If there's no acceleration, there can't be any net force acting on them, right? I guess I could just check that box right there, right? Okay, so I'm not going to let you off that easy, am I? Now, let's change it up a little bit with acceleration. So the acceleration will be 3 meters per second squared to the right. And the velocity will keep, at this instant, the velocity is 2 meters per second to the right, but there's acceleration also. So find the net force on each block. In terms of capital M. Okay, so F equals ma, right? The net force is the mass times the acceleration. And so here we have 2 times 3, 6m to the right. And for the next one, it would be 12m. And the next one, 9. And then 15. Is that right? And then 3. All right. Static friction does not match. Static friction is what is providing this this force, right? There's nothing else acting on these blocks. So so that's what's providing that force in this case. Now, in the first case, what happened was it took static friction to get the boxes up to 2 meters per second, right? But if there's no air resistance, it doesn't take anything. The boxes are going to keep moving at 2 meters per second because they have inertia. So the static friction would be 0 then. And if there is air resistance interacting with the boxes, then the static friction is just enough to overcome the air resistance and keep the boxes moving at constant speed. But the net force on the box has to be 0 if there's no acceleration. And if there is acceleration, then we have to have a net force, and that's coming from the static friction pushing on them, causing them to accelerate to the right. Good? All right, so I'll take another look at one of the problems on the exam, and then I misgraded one of them, and then I'll post solutions shortly thereafter this afternoon. Let's see, what else? Oh, static and kinetic friction. I thought we were going to get there today, but we didn't. We will get there next time. Yeah, I thought we would get there today. We will get there next time. Kinetic friction means there's motion between the two surfaces. So we have sliding, like a box sliding across the floor, right? The two surfaces, there's motion between them. Static friction, there's no motion between the two surfaces. They are static with respect to one another. There's no motion between them. Force is in newtons. Yes, we measure force in newtons. Does that mean the force? So when you draw your free body diagram for these blocks that are accelerating, you have a block sitting on the conveyor belt, and you have a static friction force pushing on it this way, and if there's no air resistance, then that's the only force, right? You have a normal force, you have gravity, but those, we don't really care about those because all we care about is horizontal motion. We know those are equal and opposite, right? So this becomes your net force. If the object is moving with constant velocity, there isn't a net force. There isn't a net force. You can have lots of forces acting on an object. So if our object is being pushed with some friction force in this direction, and there's air resistance in this direction, and those two forces are equal and opposite and they cancel out, then the object would move at constant speed, right? Because there's no net force acting on the object, but there are plenty of forces acting on the object. Yeah, friction is making these boxes move, right? Why else are they moving to the right? Because the friction between them and the belt pushing them to the right. Okay, I will stop the recording and I'll stick around to answer questions if you have some.